particle. Free particle is a particle, is a system of particle free from any interaction. Interaction energy for a free particle that is V is equal to 0, or let's call it free particle is a particle free from any interaction. Interaction energy of free particle, that is V is equal to 0. So Schrodinger equation for free particle will be del 2 psi plus 2m upon h bar square E psi, and it is equal to 0. V is 0, so only E psi will left there. In Cartesian coordinate system, we will solve this equation, Schrodinger equation for free particle in Cartesian coordinate system. This is the Laplacian term, and it can be written as del 2 del x square plus del 2 del y square plus del 2 del z square psi plus 2m upon h bar square E psi, and it is equal to 0. This is the partial differential equation of second order, and it can be solved by using the variable separable method. So before going to separate the variable, let's see what is psi. Psi is the function of a space coordinate x, y, z. So psi can be written as function of x, y as a function of y, z as a function of z. Or psi can also be written as x, y and z. Substitute the value of psi here in this equation A. While using differential for x coordinate, y and z will be treated as constant. So y, z del 2 x upon del x square plus x and z, for y, x and z is treated as constant, del 2 y upon del y square plus x x y del 2 z upon del z square plus 2m upon h bar square into E x y z, and it is equal to 0. This is the equation after substituting the value of x, y and z for psi we have. Now divide throughout this equation. Each and every term includes x, y and z, all the terms or all the variables. So divide throughout this equation by x, y and z, and we have 1 upon x del 2 x upon del x square plus 1 upon y del 2 y upon del y square plus 1 upon z del 2 z upon del z square plus 2m upon h bar square E, and it is equal to 0. Now to solve this equation, let's consider 1 upon x del 2 x upon del x square as a left side, and these all term in right side, and this will come out with del 2 y upon del y square minus 1 upon z del 2 z upon del z square minus 2m upon h bar square E and it is equal to 0. This left hand side of this equation is completely dependent only on one variable and it is x, while right hand side depends upon y and z, two variables. So this is not separated term of this equation, but we have the separated term in x in left hand side, so we may consider it as we have solved in Laplace as kx. Similarly, we may bring this y term in left hand side, and all including x, z in right hand side as 1 upon y del 2y upon del y square, and it is equal to minus 1 upon x del 2x del x square minus 1 upon z del 2z upon del z square minus 2me upon h bar square, and in place of this term we may use kx. So it is we will do it further. Again, y left hand side is independent of every terms excluding y. That means left hand side only depends upon y. So 1 upon y del 2y upon del y square can be written as ky. Let's call it equation 1 and call it equation 2. Using 1 and 2 in this equation, we can write it as kx plus ky plus 1 upon z del 2z upon del z square plus 2me upon h bar square, and it is equal to 0. For z, we may write 1 upon z del 2z upon del z square, and it is equal to minus kx minus ky minus 2me upon h bar square, and it can be written as kz. It can be written as kz. From here, there is an important result which can be obtained, and it is minus kx minus ky minus kz, and it is equal to 2me upon h bar square. Mass is universal constant and it does not depend upon any coordinate system, neither h nor e. Energy is also a scalar quantity. So we may do one thing, take E as component in x, y, z. Actually, it doesn't occur that energy can be broken in the component, but for our simplicity, we may use it as 2m upon h bar square into Ex plus Ey plus Ez. Actually, summation of this all energy is E. For x component, we have considered Ex, for y, for Ey, for z, Ez. So for kx, it is equal to minus 2 kx, we may write 2ex upon h bar square. Ky, it can be written as minus 2m ey upon h bar square. For kz, it can be written as minus 2m ez upon h bar square. Values of x, y and z of k in different equation 1, and here it was written equation 2, and for kz. Using the value of kx in equation 1, we may obtain 1 upon x del 2 x upon del x square is equal to minus 2m Ex upon h bar square. It can be written as del 2. Now we have considered only one variable, so use exact differential in place of partial differential, and it can be written as d2x upon dx square plus, when we obtain it in left hand side, 2m Ex upon h bar square x, and it is equal to 0. This is the simple harmonic motion equation, and its solution can be written as x is equal to a e to the power. It is better to write in sinusoidal equation rather in exponential. So x can be written as, and let's call it normalization constant, nx sine of 2m ex upon h bar square into x minus x naught
square the
This is the value of the displacement constant, or which we have considered, which we studied in simple harmonic square acceleration motion, that is k square x, and it is equal to, in place of k, k square, we have written only kx. So don't mislead, uh, don't get misled by this term of k square. Kx is the value of, this kx is the value of k square, and this is the value of kx, that means k. We may write for y, and it is 1 upon y del 2 y upon del y square, it was equation 2, that 1 is equal to ky. In place of ky, use minus 2m ey upon h bar square, and it is del 2, use exact differential once again, del 2y upon dy square, d2y upon dy square plus 2m ey y upon h bar square, and it is equal to 0. So y can be written as ny sine under root 2m ey upon h bar square y minus y naught. This is 3, 4.